All right, welcome to the first video where we're going to be talking about properties of gases. So to start off, we're going to be talking about three properties of gases. There are more than three, which we'll talk about a little bit later, but these are the basic properties we're going to be looking at first. Number one is they are easy to compress. Now they're easy to compress because there's a large space between molecules or particles of gas. So if let's say I have a beaker and I have gas or just air in this beaker. What you would see is you would have a bunch of gas molecules or gas particles inside of the beaker, and it would fill that space. So expanding to fill the container is another property of gas. So what you would see is these little dots would be moving around and bouncing off the container. You wouldn't see this if you had a liquid or a solid. So let's just say I had a liquid. What would you expect to see? Well, if I poured 20 milliliters of water into this beaker, what would happen is it would fill the bottom of the beaker and all of the molecules would be there. Let's say I threw a rock into this beaker. What would happen? Well, the rock would stay in its shape, and we know that it would do that because it's bonded. All those atoms are bonded together. So we would have our gas, our liquid, and our solid on the right. Okay, so large space between particles moving around, and that space makes it compressible. Some other things with gases are that the volume, temperature, and pressure of the gas are all related, and each one of those will be seen used in our gas laws in separate videos. Um, when we talk about a gas, a lot of the time we use the term pressure that the gas exerts on its container. And the pressure that the gas exerts on its container is because of the number of collisions it has with the outer surface. So I'm going to do my best to draw a little balloon. Okay, there's our balloon. Now that's pretty dang good, I'm not going to lie. All right, so inside this balloon, we can have air. So the amount of air in there is determined by how much air you put into the balloon, right? You can put a lot or a little, and according to how much air you put in that, will tell you how large the balloon is. It'll also tell you how how tough the balloon is when you put your thumb into it, how much resistance you're getting. That resistance is caused by the molecules of the molecules of gas inside colliding with the outside. So you can imagine that these gas molecules in here are colliding with the outer surface. So if this is a zoom in on the surface of the balloon, one of the gas molecules will run into it, right? It would hit it, and it will bounce off. When it bounces off, it's providing that tension. That collision hits it, um, and sort of pushes up against the side of the balloon, which gives it its strength. So the more gas molecules you would have inside of that balloon, the more taut it would be on the outside. And that's how pressure for any type of thing that's filled with air, including tires on your car, etc., is calculated by the force of the gas on the outer wall. To visualize this a little bit better, I have a little simulation here. We have gas molecules moving around in a box. And we'll look a little bit later into, how heat, temperature, and volume and pressure affect how the gas is moving, right? So we can't see gas, right? But we know it's there. We can feel it, and we can measure it. So this was what gas would look like if we would just look inside of a box right now and there was air inside. What's happening in there is a lot of the molecules are bouncing off of each other, bouncing off of the wall. And when they bounce off the wall, that's responsible for the pressure that's in the container. So what we want to look at when we look at gases is how does the gas respond to changes? So if I made the container bigger, well, the gas would expand to fill that, but now there's a lot more space in between all of the molecules. And when the molecules are moving around, there's more space. They hit the wall less times than they used to, so it will cause a lower pressure. If I made it smaller, the molecules would be hitting the wall more frequently, which means there'd be more pressure. You can do the same thing with hot and cold. So if I applied a lot of heat to this box, we would see the molecules start to take off and go a lot faster. So you can see a lot of them moving way faster. And if I were to make it cold, it would slow them way down as well. So we're going to look at these volume, temperature, and pressure individually some separate videos, but this is just an introduction to that. When you cool it down, it moves slower. When you heat it up, it moves faster. And then again, depending on the size of your container, the molecules will hit the wall more frequently, causing a higher pressure. So. The last thing I want to talk about is the units for pressure that we'll be using. So for the units, the majority of the time we're going to be using ATM, and ATM is the unit for atmospheres, which is the most common unit for pressure that we will use. We will also use torr, and we will also use millimeters of mercury. And millimeters of mercury came from when mercury was in our instruments, which is no longer a thing. So all that you need to be able to do for the problems coming up in future sections is be able to convert between these units of pressure, between ATM, torr, and millimeters of mercury. 1 ATM is going to be the equivalent of 760 torr, and that is going to equal 760 millimeters of mercury. So millimeters of mercury and torr are the same. And then 1 ATM is 760 of either one of those. So it makes it pretty simple to convert in between different units of pressure. And as always, if you need help solving for units of pressure, you can ask me, or Mr. Google does a really good job of allowing you to convert between units. It's something I ask him this all the time to help me with my conversions when I'm feeling lazy. So if you're going to do it longhand, this is how you would do it. So let's say we have 760 torr, and I want you to convert that to ATM. So you could, for this problem, just look at the top and say, okay, 760 torr is 1 ATM. But if you're going to solve it out, you'll start off by writing 760 torr. And then what is the conversion? So our conversion is here. It's 1 ATM equals 760 torr. We're going to use this as a conversion factor in order to get rid of the torr unit. So what I'm going to say is there's 1 ATM per 760 torr. And that per is going to be our division line. So the numerator is going to be 1 ATM. The denominator is 760 torr. I'm going to multiply our unit by that in order to cancel out the torr units. So I'll have 1 ATM and 760 torr on the bottom. When I do this, I am dividing torr by torr, so that cancels, and that leaves me ATM. So it's 760 times 1 divided by 760, and that equals 1 ATM. It's about the same as doing x over x when we want to get rid of our unit. Everybody knows that x over x is 1, so we're essentially just canceling out the units that we have to get to 1 ATM. And don't be afraid to use Mr. Google on this one because he does a really good job of converting our units. Okay, so next time we'll start talking about individual gas laws.